Example 3 and 3.1 deals with a real situation, talking about, in this case, the application of a polynomial functions relates to a bank vault. One really important thing is as we go forward in any math course, if you are dealing with a real situation, it often involves some kind of a restriction on the variables because of context. And in this case, because the output, the V is volume, we know that volume can't be negative. So V must be greater than or equal to 0. Now, what that really means is because V is our output, we don't have to worry about quadrant 3 or quadrant 4 because V would be negative in those quadrants. W is defined as the width of the door vault. You can make a pretty good argument that the W must be greater than 0 because you have to be able to get into the vault. But you could have, I guess it's just a steel cube at that point, where you don't actually have a door to it. So I would argue that W could be 0. And because W is the input or the X variable, this means I don't have to worry about quadrant 2 or quadrant 3. And that's really useful because ultimately what this guides me to is when I graph this function, I'm only going to make my window settings so I see what's happening in quadrant 1, not quadrant 2 or 3 because W can't be negative, or quadrant 4 because V can't be negative. All right, part A is really just making sure we understand the benefits of function notation. What they are really wanting us to do in part A is to find the volume of the vault when W is equal to 1. Now, we spent some time with function notation in chapter 1 and chapter 2. This is telling me to take V of W right here and replace the W variable with the value 1. So this is going to be 1 cubed plus 13 times 1 squared plus 54 times 1, finally plus 72. And then I can add those together. That's 1 plus 13 plus 54 plus 72. So that's 14, that's 68. 68 plus 72 is 140. Now, looking back up in the question, units matter. It tells us, if I could get there, that the volume in cubic meters, so I'm just going to throw meters cubed on the end there. All right, the second part of this, for B, wants us to find the least volume of the vault. And then what's the width of the door at this volume? We are going to learn how to do this algebraically, but not until calculus itself. So what we're going to do for this is we're going to graph our function. So you'll need your calculator. In the y1, really important that V is represented by y, W is represented by x. So V, or y, is equal to x cubed plus 13x squared plus 54x, finally plus 72. Now, I have my window on Zoom Standard because that's my default on my calculator, but we're going to tweak that. We know that x can't be negative because x is the width of the bank vault. And I know that y can't be negative because y is the volume of the bank vault. A 10-meter door is pretty ludicrous, but we're going to keep it there. We know, and I want to go back to the function, that when x is equal to 0, when w is equal to 0, v is equal to 72. So I know that we're talking about, tens or maybe even hundreds of cubic meters. So I'm just going to guess, and this is a guess, I'm going to make y max 200. I really want to stress that you have to get used to the idea that you might not get the window settings right the first time. So when I graph this, I see part of that graph at least, right? And I'd like to show you at least once that maybe it's a good idea to see the entire cubic to make sure that we're catching, all the behavior we want to see. So I'm just going to quickly change these to kind of, large values so we can make sure that we see that full cubic behavior. Oh, I changed the wrong one there. Hold on. So y min, I'm going to put the negative 200. Y max, I'll put the positive 200. When I graph this, now we can see that it is starting to look like that cubic with positive leading coefficient. It's just that all these values here have negative width doorways, which just doesn't make any sense. So I'm going to go back to my window. X min we can put to 0. X max, I think I'm going to change to 10 again. Y min, again, 0. But I'm going to change my Y max to be 1,000. Just because I did see how that graph grew so quickly. And now we get a pretty good idea of the actual movement of this graph. Now, it wants to know what is the least volume of the vault. And, very likely they want us to maybe somehow figure out that, it goes to the negative. But because of the nature of the function, the least volume of the vault is when W, or width, is equal to 0. So I'm going to put in our notes that the least volume of the vault for B here is when V of 0 is equal to 72. The problem with this is that the width of the doorway is 0 meters, which makes it pretty hard to put things into or out of the vault. right? So that is a very, very unrealistic answer. And really what we're seeing here is that the bigger the vault door is, the bigger the volume of that vault would be as well. So sometimes when we look at real situations, we can get these, that's technically valid. We could make a 72 cubic meter, square cube, metal cube, but we would never be able to get in and out of it because it no longer has a doorway at that point. So sometimes when we model things with a mathematical equation, it doesn't quite work out perfectly in reality. All right, I'm going to put the kind of full assignment here. Make sure you are checking Google Classroom because it is certainly modified on there. And good luck. Make sure you're doing these homework questions.